welcome. This is functional analysis, third session on Hahn-Banach Theorem. So we shall continue with where we left. So we had a y and an x which is in x but not y. Remember, my f was y to r, and that f of y was less than or equal to p of y for all y in y. Okay, then we define g of y plus tx to be f of y plus t times lambda, that is g of x, to be lambda, where lambda is a real number. We have to make sure that g of y plus tx is less than or equal to p of y plus tx. Okay, we have to choose lambda accordingly. That means f of y plus t lambda should be less than or equal to p of y plus tx, and assume t is positive. Remember, p is said that p of tx equal to t times p of x if t is positive. That's the only condition we know. Therefore, we assume t is positive. Therefore, lambda should be less than or equal to p of y plus tx. Let us say t lambda minus f of y. So divide everything by lambda. Therefore, lambda is less than or equal to p of y by t. See, 1 by t is again positive. So I can bring it in plus x minus f of y by t. This is for every y in capital Y. Alright. Now as t is positive, okay, this y by t, okay, as t varies, okay, as y varies, y by t, okay, as y in y is actually y. That's very easy, because if you have something like y naught, what all I have to do is I have to choose y equal to t times y naught. Right? Therefore, this is true for all y. That means my lambda should be less than or equal to the GLB. This is lambda is a lower bound for the set p of y. Therefore, this, okay, that is lambda is less than or equal to p of y plus x minus f of y for all y in capital Y. Therefore, p of y plus x minus f of y for all y in capital Y. Okay. So for each of these elements, okay, as y varies, lambda should be less than or equal to this real number. Therefore, lambda is a lower bound for this set. In particular, lambda therefore has to be less than or equal to GLB. Okay. Therefore, lambda should be less than or equal to GLB of p of y plus tx minus f of y as y varies over capital Y. So call this as 1. So this inequality we got by assuming t is positive. Just go through this proof. If you understand this, the next step will be easier. Okay, just let me pause. So now we shall get an inequality that lambda is greater than or equal to something by taking t to be negative. Okay, let us go through that argument. Now suppose t is negative, right? Then again what we need? We need f of y plus tx should be less than or equal to p of y plus tx. Remember last time we were able to pull t out because t is positive, and I can pull t out of p only if t is positive, right? So I want to do something similar. What do you think I should do then? I take t equal to minus where, therefore s is positive, right? Therefore this is f of y minus sx should be less than or equal to p of y minus sx, right? Do you follow that? This should be true for every y in capital Y. Okay, but sorry, g of g of. And what is this? This is f of y minus s times lambda should be less than or equal to p of y minus sx, right? That means minus s lambda should be less than or equal to p of y minus sx minus f of y. Since s is positive, okay, I can divide by 1 by s to get minus lambda should be less than or equal to, okay, p of y by s minus x minus f of y by s. Okay, therefore my lambda should be greater than or equal to, okay, f of y by s minus p of y by s minus x. This should be true for all y. Is that clear? Yeah, right. As argued above, as y varies over capital y by s varies over all of capital Y. Therefore, this is same as saying lambda should be greater than or equal to f of y minus p of y minus x for all y in capital Y. Right? So, if I look at the collection of these numbers, p of y minus x as y varies capital Y, what does this say? This says lambda is an upper bound for this set, right? And therefore lambda should be greater than or equal to LUB, least upper bound of all these numbers, f of y minus p of y minus x as y varies over capital Y. Okay, this is 2. So I want to choose, so call this as alpha and call this as beta, this as beta. Then what do I want to do is I want to choose lambda such that alpha less than or equal to lambda less than or equal to beta. You understand that? So call this set as A and call that set as B. Okay, so what I want is I want to choose the LEB of A less than or equal to lambda less than or equal to LEB of B. Right? Okay, choose a lambda. But there is a small care we have to take. What is that? I can choose this only if LEB of A is less than or equal to LEB of B. Do you understand this? Yeah. Suppose LEB of A is something like 5, this is something like 4. Okay, then I can't choose lambda greater than 5 less than 4, right? So I have to make sure that means, okay, is it true that LEB of A is less than or equal to LEB of B? Okay, true. If it is true, I can do that. Do you follow that? Okay. Now how do I prove that? That is, the set A is this, the set B we defined earlier. So I want to say LEB of A is less than or equal to LEB of B. Okay, how do I prove that? If you have gone through my real analysis course or book where I put a lot of emphasis on LEB, GLB, this is, you can do it within no time. What does it mean? So this is alpha, this is beta, right? Now let's start with any x in A. What is the relation between x and alpha? X is less than or equal to alpha, right? So you assume that alpha is less than or equal to beta. What does that mean? Sorry, this is GLB. I got carried over. This is GLB. Okay, but remember beta is the greatest lower bound. Therefore, this is true for every y. Do you understand this? That means if LEB of A is less than or equal to GLB of B, okay, that implies for all x in A and for all y in B, I must have x is less than or equal to y. Okay, that's a necessary condition. Do you understand that? So every element of A must be less than or equal to every element of B. Okay, right. Is it sufficient? That is, assume this. Does this imply alpha is less than or equal to beta? Assume this. So pause, review, proceed. If your LEB GLB is weak, please go through it again. Okay. Now let us look at that. Suppose assume for all x in A, so A is some real number, okay, need not be our set. B is a non-empty set, or assume for every x in A and for every y in B, I have x is less than or equal to y. Then I want to say LEB of A exists and GLB of B exists and LEB of A is less than or equal to G. It exists, both exist. And this inequality also holds. Do you understand the subtlety? I did not assume A and B are bounded above and bounded below or any such thing. It will be automatic. It will follow. Okay? Right? That is very easy. That is fixed. For example, fix for y in B. Right? So for all x in A, what do I know? X is less than or equal to y. That means y is an upper bound of A. Right? Therefore, LEB of A is, that is namely alpha, is less than or equal to y. And for which y? This is true for all y. Right? Now let's look for all y in B. Okay. Now what does that mean? This means alpha is a lower bound for B. Therefore alpha should be less than or equal to GLB, greatest lower bound of B, which is beta. Okay. Pause, review, proceed. So what have we shown now? We have shown that LEB of A is less than or equal to GLB of B if and only if for all x in A and for all y in B, x is less than or equal to y. Have you understood? Now let's go back to our set. What is my A? A is set of all. Let me just go through. I had forgotten what is A. F of y. F of y minus P of y minus x. And what was my A? Oh, sorry, what was my B? I think it should be P of y plus minus F of y. Y in B. Just make sure that I am not goofing. P of y plus x minus F of y. Yeah. Is it okay? So what I have to do? You start with any arbitrary element here. I have to prove it is less than or equal to any arbitrary element this. Right? Therefore, any arbitrary element you cannot use the same y and y here. So I will say for any y1 minus p of y1 minus x, I want to know whether it is less than or equal to p of y2 plus x minus f of y2. So this is what we have to prove. Yeah. So this is if and only if, okay, this is true if and only if f of y1 plus f of y2 is less than or equal to p of y2 plus x minus plus p of y1 minus x. Am I right? But remember, since f is linear, and where is f? F is from capital Y to R, right? y1, y2 are in capital Y. Therefore, this is additive. Therefore, it's f of y1 plus y2. Okay. So I want to know whether that is less than or equal to p of y2 plus x minus plus p of y1 minus x. These are all questions, right? But remember, f is from y to R. F has the following property. What is that? F of y is less than or equal to p of y. Therefore, this f of y1 plus y2, I know is less than or equal to p of y1 plus y2, right? Now that's easy. I want to know that whether that is less than or equal to p of y2 plus x plus p of y1 minus x. Do you remember whenever we do analysis, I always keep saying, okay, when I want to prove this is less than or equal to this, I would like to say A is less than or equal to B. I will show A is less than or equal to C and C is less than or equal to B, right? So it's enough if I show this is true. But that is very easy because this is nothing other than P of y1 minus x plus y2. That I know is less than or equal to P of y1 minus x plus p of x plus y2. But it's exactly this, because remember p of x plus y is less than equal to p of x plus p of y. That is a condition on p. Yeah. So what do you think I have proved? I have proved, okay, every element of a, okay, every element here is less than equal to any element here. Have you understood? So in particular, okay, yeah, alpha is less than equal to beta, where alpha is the LEB of a and beta is the GLB of b. Hence we can choose. Let me just make sure I'm writing that correctly. A is f of y minus p of x. Yeah. Yeah. Pause. Review. Proceed. So the hard part of analysis is already over now. It's very easy. So what have we achieved? Okay. So what have we achieved? We achieved given f from y to r, so that f of y is less than or equal to p of y for all y in capital Y, and x in capital X not in y. Then let's look at y plus rx. We saw this is a direct sum, and we extended, okay, we define g of x to be lambda, where lambda is chosen like this, lambda as in 3, right? Then what did you do? So we define g of y plus tx to be f of y plus t times lambda. Then we have shown g of y plus tx is less than or equal to p of y plus tx, not modulus, for all y in y and t in r. And so that when g is restricted to y, it is f. Okay, that is, we have extended f to y plus rx as desired. What is as desired? Okay, it is an extension satisfying this inequality. Okay, is that clear? Right. So pause, review, proceed. Now the rest of the proof is pure algebra. That was what we did in the very first session on Hahn-Banach theorem. But just to quickly recall, we will start. Okay, let us have a collection script A to be set of all, let us say zg, where z is a vector subspace of x, and so that y belongs to y is subset of z, and g is from z to r, okay, linear, so that g of z is less than or equal to p of z for all z in z, and g restricted to y is f. Okay, this collection is non-empty because yf already belongs to script A. Okay, then we want to put a partial order on this. What is the partial order? I have z1 g1 less than or equal to z2 g2. I'm sure all of you can come through, right? Remember, the most important partiality is containment, set theoretic containment. Therefore, what should be the correct one? Okay, the vector subspace z1 should be vector subspace of z2, and g2 restricted to Z1 must be G1. You should extend G1. Okay, notice that G2 restricted to Y will of course be F because it belongs to the collection script A. You understand that? Yeah, this is the partial order. Okay, check that this is the partial order. These are all very easy now. This is why I did the simplest case in the first session. Okay, and now suppose I have a collection B in A which is totally ordered, or it, as somebody calls, it's a chain. What does that mean? If I have any two elements, for every pair Z1 G1 Z2 G2 in script B, okay, either this is less than equal to this, or this is Z2 G2 is less than equal to Z1 G1. One of them must happen. That is, I can always compare any two arbitrary element. Yeah, so one of them must hold. That is, I can compare any two elements. Yes. Okay, when restrict the partial order restricted to B becomes a total order. Right. Now I want to say it as an upper bound. So how did I do? Again the same way. Look at union. Okay, Z. Okay, maybe call it Z naught, and as ZG belong to script B. Okay, as we did earlier, okay, this Z naught is a vector subspace. Okay, this is what we did in the first session, and also I said compare this with the same way we proved maximal ideal. Right? Okay, existence of maximal ideal in a commutative ring with identity. Okay, so this is a vector subspace. Right? Now what do? I have to define a G naught. How do I define G naught? So if Z belongs to Z naught, define G naught of Z to be G of Z, because Z belongs to Z naught, that means Z belongs to some Z. Okay, some Z where ZG belongs to script B. Right? So we define this way. Right? Now is it well defined? See, all these things we had already seen, okay, in this first session. Okay, yes, as seen in first session. Okay, good. Now then, what is the next thing? By very construction, remember G naught of Z for every Z, okay, is less than equal to G of Z, which is less than equal to P of Z. Right? Therefore, ZG, yeah, belongs to what? Belong to, sorry, ZC is an upper bound. ZC belongs to A and is an upper bound. Okay, the upper bound need not be an element of B. Do you remember that? Upper bound is like open interval 0 1, 1 is an upper bound, it need not be an element. Here also, when I want to apply Hahn's lemma, I have to make sure every totally ordered chain has an upper bound in the original partial ordered set. We have proved that. Okay, therefore, by Hahn's lemma, there exists a maximal element. Say Z naught, G naught in A. Maximal elements exist in A. What do we want to claim? We claim Z naught is all of X. Okay, why? If not, choose an X which is an X and not in Z naught, then now consider Z naught plus R of X. Okay, now repeat the first step. Okay, so G naught can be, call this as Z, can be extended to Z. Extended in the usual sense. What does that mean? G restricted to extended as G to Z. Okay, the extension G restricted to Z naught will be G naught, and G of Z will be less than or equal to P of Z. This is by the first step, that crucial analytical step. You understand? But then that will contradict, since X is not here, therefore I have strict inequality. Z naught, G naught is strictly less than ZZ, a contradiction. Because what does it mean? If this is not a maximal, okay, if anything is, notice that Z naught, G naught is less than or equal to ZG, right? So since it's a maximum element, I have to say Z naught, G naught equal to ZG, right? That's a definition of maximum element. If anybody is bigger than this, bigger than or equal to this, then it has to be that element itself. Okay, remember, in a partially ordered set, X is partially ordered set, and I say X naught is maximum. Okay, X naught is maximal element. That means if X naught is less than or equal to X, then X must be equal to X naught. But that cannot be the case, because Z contains an element which is different, other than, which is not in Z naught. Therefore equality cannot hold. Do you understand? So this contradiction shows my Z naught must be all of X, and my G naught, call G naught as G. Let G equal to G naught, then Xg is as desired. So we got an extension. Okay, we got an extension of F from Y to R to G from X to R, so that G of X is less than or equal to P of X for all X, right? Remember, so the major part of the proof was the one single case, namely how to extend to one extra dimension, one extra element, from Y to Y plus Rx. X is not in Y, and that's where the entire analysis was there. The rest of things are typical John's lemma argument. They are very easy. Okay, and many of you will have problem in this, and many of you already have problem in understanding John's lemma and its applications, where for example, when you wanted to prove existence of a basis in a arbitrary vector space, or existence of a maximal ideal, many times students don't really get to understand. If you are one of those guys, please go back to my foundation video. There is one or two videos, yes, especially on partial orders. In fact, I think in the first session itself I might have mentioned. I hope you all enjoyed. You can see that we can go through the proof completely, right? And notice that if you are one of those guys who are doubting Thomas, so I've chosen a lambda like that. How do I know it satisfies? You understand that I chose lambda so that alpha less than equal to lambda less than equal to beta, and I define g of y, g of y plus tx equal to f of y plus t lambda. So does this satisfy? G of y plus tx is less than equal to p of y plus tx. You can ask, right? Okay, we arrived at it, but what you do is a verification. Most of the textbooks only do the verification, but if you are one of those guys, I will just do it for you. Again, it's repeating the same proof. Now, what is g of y plus tx? If t is positive, g of y plus tx for anything t lambda. So I want to know that it is less than equal to p of y plus tx, right? But this is same as saying, is this true? But this is same as saying where t lambda is less than equal to p of y plus tx minus, what is g of y? That is f of y, because g is an extension, right? But since t is positive, that is same as saying whether t is less than equal to p of y by t plus x minus f of y by t. But notice that this is an element of our b. This is an element of b, and lambda is less than equal to every element of b. Therefore, this is a true statement. So similarly, if t is negative, do the other way around. Okay. Are you convinced? Okay. Just don't worry, just go through the proof completely. Then if you want to learn how to work, go through a typical textbook proof. That means only line by line verification. You do not know how you arrived at the proof, right? Okay, look at my book or any other book for that matter. You will get it. Okay, I hope you all enjoyed. We will meet again.